Alright, so welcome to this tutorial where we'll learn the fundamentals of pymatgen, including the structure and the molecule objects. Pymatgen is used in more and more material science and chemistry studies. It's used for scientific analysis, it's used to set up simulations, it's also used for machine learning. So in this tutorial, we're going to cover the structure object, the molecule object, and basic manipulation of these objects, as well as where to get help if after the tutorial you still need a little bit more guidance. All right, so the first thing to cover is what exactly is a structure and what is a molecule. A structure is intended to represent a periodic crystal, so it has a lattice and a basis. So the lattice will define the repeat unit of your crystal, and then the basis will say what goes inside that repeat unit. So a structure will have periodic boundary conditions, so this repeat cell will repeat infinite times. So this is a good representation for something like a solid, like a metal or a semiconductor, because these kinds of materials have like 10 to the 25th atoms in it. So having infinite atoms is a good approximation to many of such materials. In contrast, a molecule does not have periodic boundary conditions, so it's just a set of atoms in space, and there's no lattice or no periodic boundary conditions, so it basically looks like what you tell it, a set of atoms in space. So let's begin by making a structure object. There's a bunch of different ways to make structure objects. You can directly code it in Python. You can load structures from different file formats, and then you can also get structures from the internet using an API. We're going to start by making a structure using Python, but we'll also go over these two other methods in the tutorial. All right, so here's the code to define a structure in Python. The first thing we're doing here is we're defining a lattice. So this again is the repeat unit of our structure. This is the lattice vector lengths. So this is in angstroms. And then we've also defined the angle. So this is going to be a cubic cell. And then we'll define the lattice. There's other ways to define the lattice as well. This is one of the more general ones. Next, we can define the atoms that go inside the lattice. So we define the atomic identities as well as the coordinates of those atoms. And then with the lattice and the basis, we can define the structure object, print out what it looks like, and then we'll also visualize it using Crystal Toolkit. So here we can see pymatgen's representation of a structure. It has a formula, it has the lattice lengths and angles. It also has periodic boundary conditions, and you can see the list of sites on the structure, which contain what are called species and coordinates of each of those sites. And here's what that structure looks like in Crystal Toolkit. We have lead at the 0, 0, 0 position, like we defined. We have titanium at the 0.5, 0.5, 0.5 position, and then we also have oxygen at these face center positions. And the coordinates here are in Cartesian coordinates, where we've defined them in fractional coordinates over here. Okay, so now that you have a structure, what can you do with it? Well, there's many different functions and analyses you can do with a structure, but one thing to be aware of is that a lot of these functions are defined implicitly via inheritance. So what I mean by that is if you look at the code in the structure object in pymatgen, you'll see certain methods like scale, lattice, and substitute. But there's actually a lot of other things that structure can do that's been inherited from its parent classes, like iStructure, which is an immutable structure, as well as site collection, which is a parent class of iStructure. So using an IDE software can help clarify what sorts of functions are available. And let me just show that to you right now. So here in PyCharm, we have the structure object, and you can see that there are a lot of code with things that you can do with a structure, like get the lattice, do things like append, etc., insert sites, things like that. But if I look at this diagram, the structure diagram of the structure object, these methods that are in black are things that are directly coded for the structure object. But then these methods that are in gray are also available to the structure object. They just come from one of the parent classes of structure. So if I look at this inheritance diagram of structure, iStructure, site collection, etc., these methods will be defined in one of those classes, but they're still available to structure. So just keep in mind object inheritance when you look at the types of things that a structure or a molecule can do. Here's some examples of what structures can do. So structures have a composition attribute, and that composition is of type composition. So this has things like a string representation of what atoms are present in the structure, as well as the amounts that they're present in. And compositions have their own functions, like anonymized formula, where you can anonymize the elements in the formula. We can also calculate things like the density of the structure, and this is not something that we told it, this is something that pymatgen calculates, and we get the density of the structure. We can also access the different sites of the structure. So this notation is the same as saying the structure.sites sub 0. So we can see the first site that we defined was the 000 site of lead. The second site, or the first index, is the titanium site. And these sites are, again, objects, so there's many different attributes that you can call on them. For example, if I call fractional coordinates of my index 1 site, I'll see the coordinates in fractional coordinates rather than Cartesian coordinates. pymatgen structures also have various functions. For example, you can get distances between sites now that you've defined them. So for example, the distance between the lead and the titanium site is going to be 3.37 angstroms. You can also do things like get neighbors. So for the titanium site, you can say, what are all the neighbors within 3 angstroms of that site? And you can see that there's going to be 6 oxygen sites that are neighbors of that titanium. And that checks out if you look at the picture here. So there's titanium, and there's going to be 6 oxygens at these face centers that are going to be the neighbors of this titanium. Now, one of the tricky things about using structures is understanding how sites work within a structure object. So in pymatgen, structures have a lattice and a composition, which we kind of went over. Structures also have sites, which we looked at as well. And sites are positions in space, so they have coordinates, and they can also have properties. The positions in space, however, have something called a species on it. And the species can be an element, and that's what we did in our structure. At a few positions in space, like 000, we put an element like lead. But species can also have things like ions or compositions on it, and we'll cover that later. But in order to access the elements on a site, you have to use structure.sites.species for the more simpler structures, or .species for the more complex structures. And again, we'll cover this through examples, so don't worry if it's confusing at this point. So here's an example. We have the structure, our first site, and then the species on that site, and that's going to be lead. So like we defined before, our first site has lead on it. If you look at the type of this species object on the site, that's going to be of type element. So in the structure that we created using Python, we just put elements like lead on the sides. We didn't put ions or anything more complicated. And because this is of type element, we can access things that we didn't necessarily put into pymatgen. For example, we can get the atomic number of the site, so the atomic number of lead. We can get things like common oxidation states and atomic mass, etc. These are all things that have been predefined in pymatgen for lead. So once you've specified lead on the site, you can get all these other things by accessing this species object. All right, so now that we've created a structure, let's try to modify the structure and get new structures out of it. So if you want to do just basic modifications, you can do that within the methods of the structure object itself. There is another package called transformations that does more complex analyses and manipulations of structures. We might cover that in a future tutorial. Now, after modifying the structures, I'll also show you how to export them to various formats. One note about modifying structures: by default, structures are mutable objects. And if you're familiar with Python for a while, you know that mutable objects sometimes have issues in code in terms of like making them default objects in function headers, or using mutable objects in dictionaries and lists and things like that. So if you do need an immutable version of structure, there's another object called iStructure that has that. So just something to keep in mind. All right, so let's modify the structure. So what I'll do is I'll take that initial structure that we defined of lead titanate, we'll copy it, and then we'll make a supercell as our first modification. So here we go. We've copied the structure to avoid overwriting the original structure, and we've made a supercell. And now we have, 2 cells on one side, 3 cells on the other dimension, and 1 cell in the final dimension, just like we defined. We can also take our initial structure and do other modifications, like applying strain. So here I've applied a large strain in the x direction, a smaller strain in the y direction, and no strain in the z direction. We can replace sites. So this is going to replace the site at index 4, which is one of these oxygen atoms, with sulfur. So now we can see that our structure has oxygen atoms on some of the face centers, but sulfur on other face centers, just like we defined. We can also replace entire species. So we can take our initial structure, replace all the oxygen species with sulfur, and all the lead species with tin. And so here we see a completely different composition where we have tin titanium sulfide instead of lead titanium oxide. And then we can also remove species. So here I've removed all the lead from lead titanium oxide, lead titanate. And then you can also insert species. So I'm going to take my original structure, insert hydrogen at the 0.25, 0.25, 0.25 position. This first argument says, where in the list of sites do you want me to insert this site? And -1 just means put this site at the end. So it's going to be the last index site. So now I've added hydrogen to my structure as well. And then the last thing that I'll go over is how to chain these structure modifications. So we can create a new structure by copying our initial structure, and then we can chain a lot of different operations without copying them, without copying the structure. So this will actually perform in-place modifications. So we're going to replace some species, we're going to insert hydrogen, apply strain, and make a supercell. So here's the structure after doing all of those operations, and now you can see it looks pretty different than our initial lead titanate structure. Once we have the new structure, we can do things like analyze it like we did before. So here I'm printing out the new composition, and again, the composition has lots of things that you can do with it. The reduced formula is another example of what you can do with the composition, and you can again analyze things like the density or the distance to neighbors and things like that. Now, once we've created our new structure, one of the things that you might want to do is to just export that to a file format. So here's an example of exporting it to a POSCAR. And exporting structures is simple. You just give it the structure and you call the .to method on your structure, your specific structure, and you give it the file name you want and the format. And there's lots of different formats that pymatgen supports. This will print out a file called POSCAR, as well as write a file called POSCAR to your computer. And this is the file, the structure in POSCAR format. These \n's are new line characters, and in here it looks like a messy string. In the actual file that's written out, you'll see these as proper new lines. Here's another example of outputting this structure that we created, this time to a CIF or a crystallographic information file format. And here again, we can see what the CIF file format would look like, and these \n's would represent new lines that format properly in the file itself that's written out. And for both of these output functions, there are other keyword arguments that you can put in to control the output a bit more. You can look at some of these classes that will tell you what other sorts of options are there in terms of exporting these files. Okay, so now that we've gone through a basic structure example with Python, let's now load a structure from a file. In fact, we'll use the CIF file format. And we're going to do a slightly more complicated structure because this one's going to contain ions on the sites instead of just normal elements on the site. So loading a structure from a file is very simple. We just call structure.fromFile and we give it the file name, and then this will be our resulting structure from that file load. So if I print out that structure, I can see what my CIF file contained. And here it looks like the structure that we defined for lead titanate with a few differences. You can see that these cell lengths were different in our file. You can see some of these atomic positions are also offset in our file. But then one of the important things is that these species on the sites are going to be having oxidation states on them rather than being plain old elements. So here is the visualization, and again, the structure is a little bit different. You don't see the periodicity of these lead atoms because they're going to be, in a different unit cell. And then if I hover over these, you can see it says like lead 2+ instead of lead. So going to this diagram again of structures and sites and species. So this is going to be a type of structure that has species or ions on the site. So structure.sites.species is going to contain something of species type. And that species has an element on it like lead, but it also has things like oxidation state or 2+. So let's just take a look at what that looks like. So in this structure that we created from the CIF file, if we look at site 0 species, we get titanium 4+, so we don't just have titanium. If I look at the type of this species, it's going to now be a species object rather than an element object is what we had before. And then now, because we have a species object on the site.species, we can get things like the oxidation state. So this is 4+. We have access to things like the ionic radius, which pymatgen has a database of ionic radius for different oxidation sites for different elements. So you can access that. And then you can also get access to the element object if you need to. So if you need to call like the atomic number of titanium, you can do .element.z, for example. Okay, so let's do one more example of loading a structure from a file just so I can show you all the different types of species that exist on different types of sites. because this structure that we'll load now is going to contain compositions on the sites instead of elements. And this will be the most complex structure that we'll look at. So this is going to be a strontium yttrium cobalt oxide material. And if I load that from the CIF file, you can see that not only are there a lot of sites here, but some of these species have mixtures on them. So we have 70% strontium and 30% yttrium on some of these initial sites. And then we also have just 25% oxygen on some of these other sites. So what does this mean? This means that in the unit cell, if I look at some of these like half blue, half green ones, these atoms will sometimes be strontium in about 70% of the unit cells when these repeat, and they should be about 30% yttrium when I repeat this unit cell. But we don't know which cell, when we repeat this, is going to be strontium and which one is yttrium. We just know statistically what things will be. Similarly, with these oxygen sites, you can see there's 4 different oxygen positions here, each with 25% occupancy. So what that means is that oxygen might be in one of these 4 places, probably in this unit cell, but it's not going to be in all 4 of these places. And as we repeat this unit cell, we don't know exactly which position the oxygen is going to be in. So that's why there's uncertainty and partial occupancy on these sites. So to represent structures with these sorts of partial occupancies, we now have on the site a composition object rather than an element or a species object. And so now that we have a composition object, we can no longer use the species shortcut, which has a singular. We have to use the species attribute of the site. And note that you can always use species, but you can only use species if you have element or species. So you'll know if you have a complicated structure like this, because if you call the isOrdered method of a structure, it's going to be false. And false means that at least one of the sites is going to have a composition on it. For example, if I look at the 0th site and I look at whether that's ordered, that's going to be false because the 0th site was one of the mixed strontium and yttrium sites. If I look at the 20th site, that is actually ordered because that one didn't have mixed occupancy. So again, some of these sites are going to have mixed occupancy, some of them are going to be normal elements. So once you have a mixed occupancy site, if you print out the type of it, you're going to see that it's a composition object. So for example, the first site here is mixed strontium and yttrium, and it's going to be of type composition. And so the way that you can use a composition is that you can use it essentially like a dictionary of either elements or ions and their amounts. So you can say how much of it is strontium, how much of it is yttrium, and there's of course many other things with the composition that you can do to find out what elements are in it, etc., which I won't go over here. The main thing to keep in mind though is structures have sites, and then the species on the sites are complicated. They can be elements, they can be species, they can be compositions. All right, so now that we've covered all the different types of structures from files as well as making structures from Python, let's move on to getting structures from an API, and in particular from the Materials Project database, because this will give you essentially instant access to over 150,000 crystal structures. And to just throw a little bit of a wrinkle in things, I'm going to use a structure that has magnetic moments defined to show you one more aspect of these structures. So to get a structure from Materials Project, we need to use the MP-Rester module of pymatgen, or the MP-Rester class. And we need an API key from Materials Project. So you do need an account on the Materials Project website, which is free. And then once you have the account, you can go to the API portion of the Materials Project, and down here it will say your API key. So this is the string that you need to use. Now, if you create an MP-Rester object, you can use that MP-Rester object to do lots of things, but one of the methods available to you is get structure by material ID. So you need the ID of the material that you want in Materials Project. There are lots of tools on Materials Project to get you materials IDs. Probably the most straightforward one is the Materials Explorer. So the Materials Explorer lets you do things like pick elements or pick different types of filters, but then you can see that there's these materials IDs associated with the search results. So after doing a search, you can copy the materials ID that you want and paste it over here. So let's run this and see what happens. So here it's retrieving the document. So this API is connecting to Materials Project database, retrieving one structure. And here we've retrieved the bismuth ferrite material. And we can see that this looks like our normal structures. It's got sites, it's got species on the site, it's got coordinates of those species. It also has one extra thing, which is magnetic moments, which I'll talk about in a minute. Here is the visual representation of bismuth ferrite, and you can see these magnetic moments are actually being used for the visualization because some of these sites have a upspin or a downspin, and then these are attempted to be rendered in Crystal Toolkit, although sometimes the rendering can be a bit confusing. All right, so where are these magnetic moments coming from? They're actually coming from the site properties key of a site. And this is also one of the more confusing aspects of pymatgen because structures have sites, sites have species, we've covered that already. Sites can also have properties defined for them, so that's where this magnetic moment is coming. So sites don't just have coordinates, they have properties. But species can also have properties. So it can be a little bit unclear as to whether something like magnetic moments should go on the species property or whether it should go on the site itself. And this is something that even I sometimes get confused by, but in general, the guidance from pymatgen is to define things using site.properties, although pymatgen will sometimes parse output files of simulations and things and put things into species.properties instead. So we're just going to go with using site.properties for now, but again, keep in mind the species.properties also exists for certain things as well. So if I look at the site properties of this bismuth ferrite structure for site 0, which is one of the iron sites, I can see that it has properties of magnetic moment defined here. And there's other properties you could define as well. So depending on whatever you want to define for that particular site, you can put it inside here. Okay, so now we've covered the structure object. You are now an expert in the structure object. You understand sites and species probably better than even many people that have been coding in pymatgen for a while. Let's move on to molecules. Molecules are in many ways simpler than structures because we no longer have a lattice. So these are again used for systems that don't have periodic boundary conditions. And so essentially the positions that you put in are the positions that you get without any kind of repetition. So let's create a molecule using Python. It's very similar to creating a structure without having to create the lattice up front. We say what atoms are in our molecule. We also give the coordinates of those atoms, and that represents a molecule object. So here we have the formula of our molecule, we have the charge and spin multiplicity, and then we also have the sites of everything. And so the sites again have these element species on them. And here's a visual representation of that molecule. Now, just like in structures, there's a lot of things that molecules can do once you define them. And some of those things that molecules can do are defined within the molecule class itself. But then there's also other things that molecules can do that are defined in its parent classes, like iMolecule or site collection. So just make sure when you're looking for things that molecules can do, that you're also looking at things that the parent classes can do as well. So here are some examples of things that the molecule can do. Again, we can get the composition, and as we saw, the composition has many things you can do with it. IUPAC formula is another thing that you can get from the composition, so we've seen these elements reordered according to the IUPAC guidelines. And then we also can access sites just like we could in structures, and then access the species on the sites just like we did in structures. So again, this is going to be an element object for this simple molecule. Now, just like structures, we can modify molecules, and a lot of the things that you can do with structures, you can do with molecules as well. And just like in structures, there's an immutable version of the molecule called iMolecule in case you need an immutable version of this object. But one of the things that you can do with molecules that's a little bit different than structures is to add functional groups, and there is a library of functional groups that are defined in pymatgen. So you can say, here's my substituted molecule, I'm going to copy my original molecule, and on the third site, I'm going to put a methyl group. So here we go. Now, instead of having just 3 carbon atoms, we have a 4th carbon atom that's been replaced. One of the sites, one of the hydrogen sites, has become a methyl group. Now, if your desired functional group is not in the preloaded library of pymatgen, you can also define coordinates for your functional group. And this X will actually be replacing the site on which you're going to put the functional group. So if you're replacing a hydrogen site with a functional group, this X is going to replace the hydrogen, and then this is going to set the directionality of the rest of these atoms. So you can define your functional group and then take your original molecule and add another molecule or functional group on top of it. So this is just another way to define your functional groups. Finally, just like in structures, we can export molecules to various file formats. Here I'm going to export it to an XYZ file format, and this is a simple file format. Again, these new lines will be properly formatted to new lines in the file that's written out if you were to open output.xyz. And the last thing that I'll show you for molecules is just adding some bonds. You can define a nearest neighbor object that will give you a bonding strategy. Essentially, this covalent bond nearest neighbor will define bond distances for different pairs of atoms. And then you can generate this molecule graph, which will contain bond connections between the molecules depending on the nearest neighbor strategy. And there are different types of nearest neighbor strategies you can use to generate this graph. But now we can see we have some bonds defined between the different atoms here. Okay, so congratulations, you now know the fundamentals of structure and molecule objects. This is the foundation of most pymatgen usage. And now that you understand these objects properly, you'll really be able to pick up all the other pymatgen capabilities much more quickly. Now, there might be cases where you need additional code examples or additional help on these objects. The next few slides will just show a couple of ways of getting that help. The first way that you can get additional examples is to actually use the pymatgen unit tests as example code. So pymatgen has an extensive set of unit tests in its tests directory. So if you go to pymatgen on GitHub or you download the pymatgen repo from GitHub, you'll see this test directory, and then all the packages and all the different modules will have a corresponding test directory, or sorry, a test file. And that file contains lots of functions that show you things like how do you add oxidation states to a structure by guessing them. And then you'll see the syntax for doing that. Or also if you want to add a site property like magnetic moments or charge to a site, how do I add those things? You'll see a ton of examples in the pymatgen unit test. So if you need to know how to use a particular object like composition or lattice or whatever, you can look at the unit test to see a bunch of examples. A second way to get help is to actually use large language models. So language models like ChatGPT and GitHub Copilot are often capable of generating correct pymatgen syntax. You do need to check it sometimes. Like for example, if you ask it to give you the structure of bismuth ferrite in pymatgen, it's going to give you like wrong atomic coordinates and compositions. So just make sure that you are checking the results of it. But you can ask it things like, help me load a pymatgen structure from a CIF file, remove all the lithium atoms, and export the resulting structure to a CIF file, and then just skip all the boilerplate. And then it'll just give you the code to import a structure, get the structure object from a file, and then remove species like lithium, and then also export it. So finally, there's also a help forum for pymatgen, which is on matsci.org. So there's a dedicated help channel for pymatgen on this site. There are some guidelines for using this, so make sure you read that before posting here. For example, bug report should go on the GitHub issues page, so don't put bugs on this site. General questions are okay, although if your question can be answered by a large language model or it can be answered by looking at the unit tests or other examples, it's better if you do that first. But if you really can't solve something, you can also try posting it here. Okay, so that's the end of this tutorial. Hopefully you now have a solid grasp of the fundamentals of pymatgen, the structures, molecules, what they are, how do you get the species on the sites correctly, and how different analyses and manipulations of these objects can occur. This will really set you up for doing more advanced things with pymatgen in the future. So I'll try to post a few more tutorials on pymatgen on different functions and things that you can do, and I hope to see you in those future tutorials.